Okay, this is David Zierler, Director of the Caltech Heritage Project. I'm back with Professor David J. Stevenson. Dave, good to see you again.
Good to see you.
Dave, before we head to Caltech, I'd like to return to an earlier comment you made about the relative maturity of the field of planetary science at the tail end of your time at UCLA. So just to get a sense administratively, academically, were you taking graduate students? Were there undergraduates who were specifically interested in taking classes in planetary science? What did the field look, at least microscopically, from your vantage point at UCLA?
At that point, the number of people interested in pursuing planetary science was quite small. However, I think that's really true of all of science. The scientific enterprise has grown so much, and planetary science more than most. It's certainly true that there may have been more people interested in physics, more people interested in astronomy, but planetary science grew in large part because of the missions, some of which did not come along until later, Voyager in particular, the information coming back in the late 70s through the 80s, then Galileo, and then the modern era where we have so many missions. I think that has driven the field, together, of course, with exoplanets. Exoplanets has completely changed the character of the field through the involvement of instrumentation associated with astronomy. And so now you see a very vibrant field, much larger than it was back in the 70s.
Was there a graduate program in planetary sciences at UCLA?
Yes, UCLA was one of the very few that had such a program. The number of students was small.
Now, what were you doing and whose attention did you garner at Caltech when you got that offer?
I don't actually know, and I've never tried to find out, what the dynamics were at the time of that appointment. Certainly Caltech, from an early time, was involved in planetary science. Famously, the division that I'm part of made a decision back in the 1960s to get involved in planetary science. And this was controversial at the time because there was an alternative proposition, which was to get involved in oceanography. The decision was made, guided in large part by a very famous scientist, Bob Sharp, who was chairman at the time. The decision was made because of the existence of the Jet Propulsion Lab, which was, and in some senses still is, a pioneer in planetary science. I mean, in particular, unmanned. I don't mean so much sending astronauts to space, although, of course, the two are connected. So Caltech had to make a decision. Oceanography was already in place at Scripps down near San Diego, and also at Woods Hole and other places. Caltech would have been a newcomer to a field that was already recognized as being important in Earth science. We decided instead to go into planetary science. Among other things, that meant that Frank Press left Caltech and went to MIT. Anyway, we started up planetary science late in the 60s. We hired people. I came along somewhat later, almost a decade later, but it was already a well-developed activity at Caltech, tied understandably to the fact that the Jet Propulsion Lab was a world leader in sending missions to space to do planetary science.
Dave, what about the dual traditions of excellence in both astronomy and physics at Caltech? To what extent did both of these endeavors drive Caltech's early interest in planetary science?
As best I understand it, they did not have a big role to play in the decision. The decision was very much centered within what was originally a geological division and then became geological and planetary science, which is our current title. My understanding is that the reason why astronomy and physics played rather little role is because, at least in astronomy, a lot of the attention in the 60s, for example, was outside of our galaxy. It had to do with the universe as a whole. It had to do with quasars, which Caltech led in the understanding of. These were things that were disconnected from questions that have to do with the origin of the solar system, with meteorites, with planets, and so forth. And so we were not getting a great deal of support in our drive towards doing planetary science. It's important to remember that Caltech is small and we make choices. And I support that. I think that's a good idea. You make choices, you don't try to do everything. And so the astronomers had their own agenda of what they thought was most important. And for the most part, it did not include planetary science. I'm exaggerating slightly because there have always been people at Caltech who have interests that overlap with planetary, and I knew them. I'm talking about people like Neugebauer, no longer alive, who was chair of physics, math, and astronomy at one point, and was a pioneer in infrared astronomy. And infrared astronomy has played an important role in understanding planets. So, of course, there was some overlap, but for the most part, it was, as I said, an activity that began connected to geology as it is now, rather than an activity driven by astronomy.
Who was it at Caltech that reached out to you?
So the person who made the offer to me was Barclay Cam, and Barclay was a quintessential Caltech person, meaning that he had spent his entire career at Caltech. He came to Caltech as an undergraduate. He aspired to be a theoretical physicist. He was seduced over to astronomy, to geology, and eventually became chair of our division after Bob Sharp ceased to be chair. Barclay was chair of our division for a long time, about 11 or so years, and he was the one who made the offer. There were other people connected to the division who were evidently enthusiastic. For example, Pete Goldberger, who was also connected strongly to astronomy and physics, but it was essentially the geological and planetary science division that sought me as a faculty member.
Now, were you happy at UCLA? Did you jump at this offer right away? What were your reactions to this offer?
So I thought UCLA was quite good. I could tell that it had some outstanding people. It still does. The average is not as high. In other words, there's a spread in abilities of the faculty. I could tell also that a lot of the students who went to UCLA had no particular interest in being outstanding in any area of science that I was interested in. When I looked at Caltech, I saw something different. I saw a more universal excellence, and I saw outstanding students, and I liked the smallness of the place. But to come back to your question, I was happy enough at UCLA. I was happy enough at the West Side. I did not immediately jump at the appointment. I visited Caltech. I saw for myself how outstanding it was. It was easy to visit, of course. I just hopped in my car and drove across the valley. So I could see that Caltech was the right place for me, but I did not immediately make that decision. I took a couple of months doing so.
Why ultimately did you decide to accept the offer?
I decided to accept the offer because I could see that Caltech was the best place in the world to do planetary science.
Now, did you physically move your house, or was it convenient enough for you to just stay put?
I physically moved. I had an apartment on the West Side, and then I moved to an apartment and eventually a condominium in Pasadena, or in fact Altadena, which is next door.
Now, is your current appointment, in terms of where you're housed administratively at Caltech, is it the same as when you first joined?
It is indeed. I think there could have been an option to get involved in other divisions. I chose not to. Some people have felt that that was something that would work for them. I think in the end, I've done the right thing. I have had, at least in recent years, access to outstanding students. I think getting involved with both undergraduates and graduates at Caltech has been one of the pleasures of being at this institution.
I've heard so much about the culture of interdisciplinary studies at Caltech. Did that strike you at all when you got here, that there would be things that you could discuss with professors who might not necessarily be as centrally focused as the things you were working on?
Certainly there was that opportunity, and you did not see it so much at UCLA. UCLA is a very large place, and there is something that happens when you're at a very large place. It even happens a little bit at Cornell, although I think Cornell is structured better than UCLA in terms of people talking to each other. But when you're at a large place, there can be a sense of isolation. It's almost paradoxical. You have a big place where you feel alone and a small place where you feel connected. I do think that for the most part, people work hard doing their own thing and don't actually spend a lot of time talking to other people. But at Caltech, it was possible. I went and still go to physics colloquia and to astronomy talks, not all of them, but many of them. And I have chance meetings with people and did have meetings in the past with people that you might not have encountered if you had been at a really big place. I'm talking about Feynman, who I talked to, Ed Lewis, who was a Nobel laureate in biology, who I used to have lunch with, and so forth. So Caltech benefits from being small. There is this opportunity to talk to people across a wide range of fields, and physical smallness also matters, because it means that when you're walking across campus, you might see someone who is in a different field, but you know who that person is. And that was true with the people I just mentioned, that you could encounter them just when you walked across campus. You could also encounter people who were running the place, like the president of Caltech. The person after whom my chair is named is somebody I can remember meeting just by chance, Goldberger, just by chance walking across campus in the 1980s and having a pleasant conversation with her. I think that would be unlikely to happen at a big place.
Did you take graduate students along with you, or you were looking to build up a group from scratch when you arrived at Caltech?
I did not take graduate students along with me. I worked a little bit with graduate students at UCLA, but my style of science has never involved working with a lot of students. And frankly, the students at Caltech are of higher quality anyway. So I was happy to leave UCLA and come to Caltech and become involved in working with students here.
And what were your early interactions with JPL? I'm curious, given how important they were to the push in planetary science for Caltech.
My style of doing science does not actually require very strong interaction with JPL. I am was in some sense a parasite, meaning that I benefited from the data that were returned from spacecraft, but did not get involved in the acquisition of that data. I did not get involved in the people who were developing the missions, developing the instrumentation, and so forth. My approach to science was more, shall we say, ivory tower. So JPL was there. I think we benefited from it in the sense that students saw the value of the place, but in a strange way, it didn't actually have a huge impact on the way I did science.
In what ways were you following the Voyager spacecraft mission? What was important for you at this point as you arrived at Caltech in the early years?
I think Voyager was very important. Certainly, I can remember the experience of seeing the news conferences that were held at JPL, where the data from the mission were presented to the general public and discussed. Scientists who I knew were involved in those presentations. And this was the way you learned about the exciting new discoveries. I can remember being here at Caltech in the middle of the night, seeing for the first time images of satellites that we had never looked at before. This came somewhat later when the Voyager mission got out to Uranus or Neptune, and we saw for the first time, for example, Miranda, which is one of the satellites of Uranus. And that was breathtaking because you were seeing remarkable pictures of a surface that you had never seen before. So there was indeed an impact to my science that came about through those missions. It influenced the choices that I made about the subjects that I got interested in. I was still interested in the giant planets, but I got interested in Io and Europa and Ganymede and Callisto and Titan and so forth. And those interests were driven in large part by the NASA missions, especially Voyager.
What was known at this point, and how did your research contribute to these findings regarding the existence of ice or even water outside of Earth?
So that's actually a complicated story. When people first started thinking about icy satellites, large icy satellites, like Ganymede, Callisto, Titan, Europa is somewhat special, it's mostly rock, but has ice on top. When people started thinking about that, there was a group that I was not part of, involving people such as Stan Peel and Pat Casson. I knew these people, of course, Ray Reynolds. I knew these people, but I was not directly doing research with them. They were saying that there was water underneath the ice. And in the 1980s, the picture moved a bit in the recognition that ice could convect, and that as a consequence, the water could go away.
What does that mean, ice could convect?
Ice as a solid can undergo convection, thermal convection, carrying the heat from inside the body to the surface without ever melting. So you had the equivalent of glacial flow. And that, in fact, is what these people were saying, that unlike even earlier ideas, you might actually have solid ice. And I got involved in this subject at a time when it still seemed possible. Subsequently, towards the late 80s, it became apparent that ice might not be quite efficient enough, and so you could have water. And that is the current situation. In the case of Europa, we have a special circumstance where it seems likely, perhaps helped by tidal heating, that you have an ocean underneath the ice. And that was already the view at that time. I had a student who worked on this issue, constructing models of what the ice might be like on Europa, how thick it might be, what the temperature variation might be, and so forth.
Despite those particular characteristics, just to be clear, when we're talking about ice and water on places like Europa, is this H2O? Is this something that we can cool our cocktails with if we had the ability to do so?
Yes, it is indeed H2O. When you get further out in the solar system, there are more exotic ices, if you will, other materials. I was a big fan, I still am to some extent, of ammonia. Ammonia is hard to see. It's much less abundant, but it has an important role to play, perhaps in ice volcanism, because ammonia, when you mix it with water, that's basically cleaning fluid, has a lower freezing point than pure water ice, much lower. And so you can have liquid in a body at a temperature well below the freezing point of pure water. So other constituents matter. Methane matters. Methane is not as abundant as water, but more abundant than ammonia. In the outer reaches of our solar system, you also have nitrogen ice, carbon monoxide ice, perhaps other things.
What was some of the initial excitement about discovering ice and water beyond Earth? Did it center around the possibility that non-Earth planets or satellites could support life, or was there something more fundamental at play?
I think at that point in the 1980s, or even more recently, people were not talking that much about life or about the role of an ocean in supporting life. My sense is that that's a more recent idea. It is, of course, true that people knew even earlier that when you had liquid water, you had a host for a variety of chemicals that could dissolve in the water. You had an energy source, and so you might have the seeds of life, because what you need is an energy source and a certain level of complexity, and that could indeed come with a water ocean. There were certainly ideas already in the 80s that centered around Europa. That was an attractive possibility. But the enthusiasm about life in oceans outside of Earth seems to me to be something that happened a bit later and wasn't heavily pushed in the 80s. I'm not sure, to be honest, that this is something that is so new. I think that this was always there. Planetary science is, after all, in part a political enterprise, and so you seek support from the general public, and the general public gets excited about life elsewhere. So naturally enough, this becomes part of the rhetoric that people put forward in support of the science that we do.
Dave, tell me about your proposal, along with others, for the existence of an ethane ocean on Titan. What were some of the advances in instrumentation that made that proposal feasible, and how well has that aged over the years, that initial idea?
So that was actually an interesting story in that it shows how a graduate student can play an important role in creating a bridge that might otherwise not happen between faculty. The student in question was Jonathan Lunine, who is now a professor at Cornell in the chair that Carl Sagan once occupied. And Jonathan and I were working on other things. He was really the first student I had at Caltech. And he commented to me one day that another professor who was literally yards away, Yak Young, had worked on the fact that through photochemical processes, methane, which we knew to be abundant, was converted to ethane and other things on bodies such as Titan. I did not know much about photochemistry, but I got intrigued at that point. There are other things we now know that get produced as well as ethane. But ethane, which is C2H6, is a liquid under the thermodynamic conditions on Titan. And so I could see immediately that there might be a conversion from methane, which is known to be present in the atmosphere of Titan based on work by Gerard Kuiper way back decades earlier. So we knew it was there. It's being converted to ethane. It should rain out on the surface. And so over geologic time, there should be a conversion and the conversion should be the equivalent of a kilometer thickness of liquid. It is in the liquid state under the relevant conditions. And so then you might have the global ocean. I can remember even going with Jonathan across campus to the chemical engineering library at Caltech. In those days, there were branch libraries that were useful, and looking up the phase diagram for ethane and methane, perhaps with only limited success, but starting to get an idea of how things work. To be sure, there were people elsewhere outside of Caltech who had also been thinking about the photochemistry. But we did come up with this idea that there might be oceans on Titan. It's not right, although interestingly, it still affects the way people think about the surface of Titan because of the puzzle of where is the ethane. So the story is probably more complicated. That's often true in science. But it was an interesting illustration of how information that became available through spacecraft missions, but also through modeling, drove a development in our understanding. I'll be honest with you, I don't actually remember anymore the extent to which there was a connection between that effort and the new data coming back from Voyager. There was certainly some information, and it was indirect because what Voyager did for us was actually find the surface of Titan. We didn't have that before. So I think that's the answer to the question of where's the connection to the spacecraft mission. I think it is in the recognition that through radar, we actually found the surface, and so we could characterize the surface conditions. And so that was very important. But a lot of the ideas about conversion of methane and so forth had already been circulating amongst scientists. By the way, it happens in Earth's atmosphere as well. If you read about global change on Earth right now, what you will read is that people are concerned about methane because it is released from natural gas, so biological origin, of course, on Earth, unlike Titan probably. And then I saw it in the New York Times just last week. Somebody said correctly, well, methane doesn't stay around. And they're right. There's actually a residence time because methane is continuously broken down by UV photons from the sun. Carbon dioxide, on the other hand, which is the main concern, continues to accumulate, modulated only by the ability of that gas to be ingested by the Earth's oceans. So you can see ideas that come up in the understanding of planets also affecting our thinking about the Earth.
Dave, a broad question at this point about the powers of extrapolation. Once you start to think about and have the ability to verify or not the existence of ice and water beyond Earth, how easy or not is that a leap to ice and water on exoplanets, or just the very idea that there might be exoplanets out there that might not be very different from the ones in our own solar system?
Well, certainly the idea that liquid water might be common in our solar system. Common meaning that we would find it beneath the very cold, icy shell of bodies. That does stem from a theoretical understanding of the ability of ice to carry heat, along with the recognition that there are constituents that function as antifreeze. I've mentioned that already in connection with ammonia. And that, by the way, is why I advocated 20 years ago, maybe even more, that there should be oceans in Pluto, oceans in Triton, possibly oceans in small satellites and so forth. When it comes to exoplanets, in some ways the issue is a little different, maybe, because so far, a lot of these bodies that we've found are actually fairly hot, and we don't know much about how much water they have. Water is certainly the most, or should be, the most abundant condensable material in the universe, simply because oxygen is the third most abundant element. And in the presence of a lot of hydrogen, you should have water. And that is expressed in our solar system. It's actually not so clear for the rest of the universe. But to get to your question, from a theoretical standpoint, it would seem reasonable to suppose that water is very common, that water in its liquid form is also quite common. A lot of it may be dissolved in hot rock, and so it may not be the everyday idea of liquid water that we have on Earth that we can drink. I am not so sure, actually, that so many of the exoplanets are like Earth. But the number of exoplanets is so enormously large that, of course, only a small fraction of them need to be like Earth in order to have a lot of Earth-like planets.
Dave, at this point, Caltech, mid-1980s, where is geophysics in your overall research agenda? And does it change as a result of you coming to Caltech?
I've always been interested in geophysics. I've always been interested in particular in how Earth has a magnetic field, in how Earth gets rid of heat, which has to do with convection. So I had a natural interest in Earth's core. I was a recognized participant in discussions, papers about how Earth's core worked. So that was beginning already at UCLA. It continued at Caltech. I did see planetary science as an opportunity to skim the cream. Planetary science certainly was, maybe even still is, less mature as a field. And that gives you greater opportunity for the kind of science I do. It means that you can do what I call skimming of the cream, identifying things that people haven't done yet, getting in first simply because it's not as well developed as a field. My way of doing science fits less well with the very mature development of, for example, the structure of the Earth, the composition of the lower mantle, and so forth. So I find these things interesting, but I fit less readily into the community that do these kinds of things simply because they are getting into the detail and I'm less interested in detail.
How did you get involved in questions about the origins of the moon, and what orthodoxies about its origins may have needed to be revisited at that point?
So I cannot claim to be a leader in working on the origin of the moon, even though I helped run a conference and played a significant role in conferences from the beginning of discussion of this subject. By coincidence, by chance, I was present as a student at the meeting in 1974 where the currently favored idea was first discussed, as best I can tell. This was a meeting at Cornell. That's why I was there. It was a meeting on planetary satellites, which was not my interest at the time, but because it was at Cornell, I attended. And the idea was put forward by Bill Hartman in a conceptual, phenomenological way of possibly having large impacts on the Earth as it formed. It was developed much more quantitatively by Al Cameron, who was already involved in the subject and was at that meeting. Al Cameron was a professor at Harvard who I knew quite well, and also Bill Ward, who was actually a Caltech student at that point, working with Peter Goldberger. And indeed, Cameron and Ward put forward the ideas that quantified the giant impact of the moon in the same era, that is around about 1975, 76. So I already knew about the subject at that point, but was not working on it. The really big thing was 1984, and it was a meeting I attended. It was in Kona, Hawaii, and it was the closest you come in science to a revolutionary meeting, because you saw a major shift in the way people were thinking about the subject. I had already been thinking about it, working with a Caltech undergraduate called Chris Thompson, who is now a professor. So Chris and I had worked on ideas of the giant impact and what happened when material was put in orbit and coalesced to make the moon. And so I turned up at this meeting in Kona, Hawaii, unaware that other people had reached a similar conclusion. And so you had this interesting phenomenon that sometimes happens in science, where people come forward with a common idea that changes the perspective of the field. It was resisted by some people, rightly so, because there are issues that are still unresolved about the chemistry. And so it was resisted by some chemists in particular, and I think they were right to resist it. I remember Ted Ringwood being concerned about it, Mike Drake being concerned about it. These people are no longer alive, but they were prominent geochemists of that era. But Al Cameron came forward with the initial attempts to do simulation of the formation of the moon by a giant impact. I presented some work on analytical approaches. Other people were commenting on this. So out of that came an effort that changed the perspective of the field. Somebody who was too young at that point to directly contribute, but later became a central figure, was Robin Kenner, who actually was a visiting professor at Caltech at one point, but who much later and at present is a distinguished scientist working at the Southwest Research Institute in Boulder, Colorado. So Robin was very important to the story. There were other people who were important later on. The story is not fully resolved, but the idea of a giant impact is persisting, and I think it is correct. And it is not just important for understanding the formation of Earth's moon. It is an aspect of the way we think about the formation of planets that pervades all of our ideas of planetary formation. It is also an exasperating subject because it becomes a sort of universal panacea, something that you invoke when you don't understand what's going on. And so you can always say, well, that was a giant impact, and it did this and that, and who can tell? So it's not an entirely satisfactory theory, but it's an important idea.
What are competing theories, if not the giant impact?
So the competing theories largely subsided at that 1984 meeting. They were present in a prominent way at earlier times. One of the ideas was capture. Capture was never that popular, actually, but it sounds like a good idea. It sounds like a sensible thing to say that the moon formed somewhere else and the Earth just grabbed it, and it ended up in Earth orbit. That is possible in principle, but it fails to explain what we see in many different ways. From a purely physical point of view, capture is actually exceedingly difficult. And the reason is elementary physics. If something falls into the Earth's gravity field from great distance, then unless you impede its motion by putting some stuff in its way, friction, if you will, unless you impede its motion, it will come in on a hyperbola and it will leave on a hyperbola. You do not capture using gravity. Gravity is conservative force. And you might say, well, okay, I can put stuff in orbit that will act as friction, but then you get into trouble because in most cases, if you try and do that, you get a disaster. You get too much friction and it ends up coalescing with the Earth. So it's a neat trick to put something in orbit, and a giant impact succeeds in doing that. The other idea that was actually fairly popular was co-accretion. Co-accretion just simply meant that as you were aggregating stuff to make the Earth, you were simultaneously aggregating stuff in Earth orbit. This turns out to be difficult to pull off, and the main reason is angular momentum. When you are adding small bits of material together to make a body, it's difficult to create the spin that you see. The spin tends to average out to zero when you have a lot of small bodies coming together, some from the left, some from the right. There's no special sense in the motion of solid bodies. This is not true, by the way, for gas. So it's not true for Jupiter, for example, but it is true for making something like the Earth. So the advantage of the giant impact, which was really the key idea that Cameron and Ward put forward in 1975 or 76, the advantage is that a single impact of a Mars-sized body would explain the angular momentum of the Earth-Moon system, which basically meant the initial spin of the Earth. Of course, right now, most of that is expressed in the orbital motion of the Moon about the Earth. The Earth is now only rotating every 24 hours, but early on it was rotating once every 5 hours, or some people have even suggested once every 2.5 hours, which is near rotational breakup. You do that through giant impacts.
Dave, I'm curious if manned missions to the Moon, collecting samples, simply being there, was helpful in a way that studying other satellites would have been, by definition, more provisional in terms of how they were formed.
I've never been a big enthusiast for manned exploration. I understand, of course, the tremendous benefit that can come from putting a geologist on a solid surface, collecting rocks and bringing them back to Earth so that we can study them in the lab. Of course, you can bring rocks back without sending a person, and we're doing that for Mars right now. Jack Schmitt, who was the only geologist to ever actually be on the Moon, is somebody that I met. He came to Caltech. He was known here. He was a student here in geology, although that was before my time, but I met him later. So the Apollo program certainly had some impact on the data that we had for understanding the Moon. But interestingly, a lot of the ideas that have emerged about the way the Moon formed could have developed without having the Apollo program. You certainly needed to know about the fact that high temperatures were involved. That was evident from the North Pacific crust. You needed to know some of the other things that astronauts found, but these could have been obtained through unmanned missions. So I don't think that manned missions are particularly important. They are very expensive. It is very expensive to send people into space. I'm expressing a view that is not special to me. It is common within the planetary science community for people to say that unmanned missions are the way to go for exploring the solar system. The idea of sending people, whether it be to the Moon or Mars or whatever, is a romantic notion. That doesn't mean it's bad, but it has to have some other justification. You're not, in my opinion, going to justify sending people to space because of the science that they can do.
Dave, of course, another major event in 1984 was you winning the Harold C. Urey Prize, and I believe, if my notes are correct, being the inaugural holder of that prize. What did that feel like?
Well, it was nice to be recognized that way. Of course, since it was a new award, it was hard to know the significance of it. It has, of course, become the planetary science equivalent of the Junior Scientist Award that you see in other societies. So, yes, it was a pleasure to be involved in that. Maybe I did not think of it as hugely significant at the time simply because it was completely new.
Now, being that it's within the Division for Planetary Sciences of the American Astronomical Society, is the AAS your home society, so to speak, or are there other planetary science societies out there?
When I was a student at Cornell, the time came to figure out what society to belong to, and I actually applied to become a full member of the American Astronomical Society in the mid-1970s. At that point, the Division for Planetary Science was very small indeed, as indeed it still was into the 80s. And I remember getting a letter back saying, do you really want to be a member of the American Astronomical Society? Because it cost more money, and I guess they were unsure about why I was doing this. I did it. So I am, in fact, a full member of the American Astronomical Society, and also became an affiliate member for the DPS. In the late 70s, I attended meetings of the Division of Planetary Science, and in the 80s as well. In the late 70s, everybody easily fitted into one room. So it was a small activity. That's the one that made sense. But actually, I have always had a strong connection, you might even say a stronger connection, to the American Geophysical Union, which of course is much bigger. So the American Geophysical Union has a section on planetary science. I was even the president of that section at one point. And planetary science has become an increasingly larger part of the American Geophysical Union. AGU, as we call it, is an enormous organization. I've lost track of how many members it has. Absolutely huge. It is very inclusive, and so it has opened itself out to all manner of related areas, including things that might most naturally fit with the Geophysical Society of America, including things that are done by people in Europe and in Australia and so forth. And so it has become truly international. It has been very successful. It has very well-run meetings. It runs publications and so forth. So AGU is very big, and I was involved in that from the early days as well as DPS. I have not attended the regular American Astronomical Society meetings, except the very first one that I went to when I was a student at Cornell, which would have been in Rochester about 1973 or 74.
This dual membership, I wondered the extent to which it's a microcosm for something broader about planetary science, and that is, it's not a field that should have its own scientific society because it's so multidisciplinary, if you will.
Well, I think historically, at least, the Division of Planetary Science has as its core people who are interested in the parts of planetary science that fit naturally with astronomy. Of course, it has spread out more in subsequent years, but it's still true that a lot of it has to do with atmospheres and with those parts of planetary science that fit naturally with astronomy. There are other kinds of planetary science. You're right. Planetary science, I once had to write for an encyclopedia an explanation of what planetary science is. And I began by saying that planetary science is an indiscipline, meaning that it's not a discipline, or an undiscipline, meaning that it's just a combination of everything that everybody does that normally gets labeled as geology or geochemistry or geophysics, or geobiology or whatever, but applied to planets. And that's still true. So yes, it's true that there are other avenues that are available to people who do planetary science. There's one other very important one that I haven't mentioned, which I was also involved in, less so now, and that's the Lunar and Planetary Science Conferences, which initially were inaugurated for the people who studied the return from Apollo. So these began as meetings at Houston. When I first got involved in it, it was still held at the Johnson Space Center, south of Houston. And so I attended those in the late 70s. and I attended quite a few more in the 80s as the meeting evolved. It is still held every year in Houston, different location, but very much tied historically to this notion of understanding planets from the point of view of the materials, because after all, that's what you do when you look at Apollo rocks. Like everything else, it has spread out, it has become broader, covers a wider range of things, but it's still true that the core of LPSC, as we call it, is the people who study the materials, such as meteorites.
Can you talk a little bit about the early high-impact flux on Earth? What is that, and what were your findings regarding the way that it may have delayed the origin of life on Earth?
So, back in the 70s and 80s, and maybe even more recently, there have been many speculations about the delivery of material to the Earth. I think it's fair to say that it is still an unresolved issue. Certainly, in respect of starting life on Earth, I posed that issue as a project in the class that I taught at Caltech. I am fond of creating term projects for students, and some of these term projects end up as published papers. And so it occurred to me that since impacts on Earth were known from around about 1980 to have a potentially important consequence for the development of life, I'm referring, of course, to the famous incident, which I was not involved in, but observed, of the supposed impact that got rid of the dinosaurs, the demise of the dinosaurs 65 million years ago. Still somewhat controversial, but we know that there was an impact. We see the crater in Chicxulub in Mexico. So there's no question that there was an impact at around about that time, and it had a major consequence for the Earth. It may have acidified the ocean, it changed the atmosphere, it caused global fires. So we knew a whole bunch of things. These were things that we learned in the early to mid 80s. So given that context, it was natural to wonder, well, if the development of life on Earth can be so much affected by impact, why not consider the possibility that the origin of life on Earth was delayed or greatly affected by the greater flux of impacts early in its history. And so that led to the idea that you could have had a scenario where life began on Earth and then, so to speak, got hit on the head. You could then imagine life starting over several times before you finally reached a point where the flux of impacts onto the Earth had diminished sufficiently to allow life to persist. Why was this an attractive idea? Well, it was in large part the recognition that impact flux had certainly been larger at earlier epochs. How did we know this? We actually knew this from looking at the moon. And this was the work of Gene Shoemaker. Gene Shoemaker, by the way, was division chair at one point at Caltech. He is somebody that I co-taught a class with, so he was associated with Caltech when I came to Caltech for a while, although he was also at Flagstaff. He was the world's leader in understanding impact flux on the Earth. And he said that throughout most of Earth history, the flux has been low and rather constant. It's not clear whether that's true, actually, but that's what he was saying. And then at an earlier epoch, marked in substantial part by what is called the late heavy bombardment on the moon, which was 3.8 billion years ago or earlier. In that earlier epoch, extending back to the formation of the Earth 4.5 billion years ago, there was a higher flux. You could naively imagine some exponential tail of formation of the Earth, extending from 4.5 billion years ago to 3.8. That was the basis for the idea that the Earth was hit by things, some of which were quite big and could destroy life so that it had to start over. So that was sort of attractive. I also knew, actually from my time back at UCLA, that some people thought that life was easy. What they meant by that is that the beginnings of life were accomplished on a rather short time scale, geologically speaking. We don't know this, by the way. I had a conversation with Stanley Miller of the famous Miller-Urey experiment at the University of Chicago. He was part of a group that I got involved with at UCLA. And we met in a restaurant in Westwood, Stanley Miller and I and some others. And I asked Stanley, how long did it take life to begin on Earth? And he said, 1 million years. Of course, he didn't know. Nobody knows. And so this was sort of a joke, but it wasn't entirely a joke, because what he was saying, in effect, was that it couldn't be really long, because the evidence that existed for life on Earth already suggested that life was complicated 3.6 billion years ago. I'm talking about what we now know in the geologic record to be stromatolites. These are algal mats from Western Australia, for example. So we knew that life could be quite complicated at 3.6. And we also knew from people like Jerry Joyce, who I also know, down near San Diego, that if you try to manufacture life in the lab, it's not so easy. You don't get things crawling out of the test tube. So it can't be really, really short, but it can't be really, really long either. And 1 million years fits in between. But given numbers like that, 10 to the 6 years is tiny compared to the age of the Earth. It's even tiny compared to 1 billion years. So why not imagine a story where there was some delay in developing life on Earth, but once it developed, things could happen quickly. I have to say, having talked to people who study the subject of the origin of life, that it's not at all clear that these stories are the right way to think about it. I have to also say, in respect of that particular work, that by coincidence, we were thinking about this problem at the same time as people in the Bay Area. I'm talking about Norm Sleep, who is at Stanford, Kevin Zandley, I know these people, Kevin Zandley at NASA Ames. They actually wrote a better paper on the subject. Both of us ended up being published in Nature. Norm Sleep even suggested to me that we get together and do it jointly. At the time he made that suggestion, we were far enough along in what we were doing at Caltech that we went ahead with what we had. But frankly, they did a better job on the problem. I think it's a fascinating idea, impact frustration, the origin of life. I don't know whether it's right.
Dave, what about approaching the issue from the diametrically opposed position? As we said in an earlier conversation, what about looking at these high-impact events as a source of life, either with the delivery of microbes or bacteria, or alternatively, what about the possibility that these high-impact events change the chemical composition of the oceans, for example, that would have made them hospitable for life in a way that they might not otherwise have been?
Well, we're in the realm of speculation where you can say almost anything and there's no obvious contradiction. Sure, it's possible. I do, however, know enough about impact physics to be skeptical about the notion that impacts are a way of starting life, at least in respect of big impacts, because when a body comes in, as it must, at least 11 kilometers per second, because it's falling into its gravity field, it's horrendous. You get vaporization, you get high temperatures, you get a shock event that is spectacular. Who knows what the consequences are far away? Maybe you could even conjure up some story where they're good, but On the face of it, it's not a very attractive idea. Meteorites, different story, because meteorites slow down high up in the atmosphere. They hit the Earth's surface essentially at a velocity that is set by air drag. And so they're not moving particularly fast. They make a small hole in the ground. They're hot enough that you wouldn't want to pick them up immediately, but they cool off quickly, and the center part of a meteorite actually stays cold, even after passing through the atmosphere. So there's no doubt in principle that you could deliver stuff from elsewhere that's survivable and is suitable. I look at the problem and I say to myself, well, the early Earth is complicated in many different environments. There's the whole periodic table to play with. Why invoke things from outside? I don't see a good argument for doing so. But of course, like everybody else, I'm ignorant.
Dave, tell me about your work with Hugh Davies on subduction zone volcanism. How did that get started?
So that work is a curiosity in the sense that it is quite well cited, but is not central to my research effort. The way that began was actually with another person who was a very good student, David Scott, and it concerned melt migration. I got interested in the problem of what happens when you take a rock and start to melt it. The melt being typically less dense, not always, but usually less dense than the rock from which it's formed, tends to migrate upwards, tends to percolate, just in the same way as water percolates through coffee grinds. And I got interested in the theory of that. As it so happens, contemporaneously with that effort, Dan Mackenzie at Cambridge in England was doing something much more complete. But we did end up doing some significant work on melt migration as applied to mid-ocean ridges. Hugh Davies was a very good student in geophysics. Another one of my geophysics students, David Scott, was a geophysics student. And Hugh picked up on the other obvious possible application of melt migration, which is subduction zones. So that work was very much driven by him. It was his choice. It was not something that I gave to him. It was something that he realized would be a natural direction to take that kind of work. And so he developed some very nice ideas about how melt migrates above a subducting slab. This, of course, is the origin of arc volcanism, the kind of volcanism we see with the Cascades in northwestern US, volcanism in the Aleutian Islands, volcanism in Japan, New Zealand for that matter, many places, South Africa, South America, not South Africa. So this is a common thing associated with places where materials going back down into the earth, material that might include some water, and so part of the story had to do with the role of water. It's an interesting story. I don't think we really understand yet fully what's going on, but it is a good example of an interdisciplinary subject where you're trying to combine geophysical ideas that come from fluid dynamics with geochemical ideas that come from looking at the composition of the rocks that make up the volcanoes in island arcs.
Dave, a question that's not germane to your immediate field of interest, but just by dint of what you were studying and where you were, what was the day like for you when the Challenger exploded in January 1986? Do you have clear recollection of that? And more broadly, how did Caltech and the associated research communities respond to this tragedy?
So I remember it well for several reasons, actually. On the night before the Challenger disaster, I had an extended conversation with Feynman about Earth's gravity field. And that's not directly connected, except, of course, that it was the last time I had a discussion with Feynman, because he got involved in trying to understand what happened after the Challenger disaster. So in that sense, it had a major consequence for some of the things I was thinking about.
What was the nature of the discussion with Feynman? What were you talking about?
So that was an interesting story. It was the only occasion I can recall where Feynman contacted me with no forewarning. What I mean by that is that there were a small number of other occasions where it was natural to talk to Feynman because we both got interested in something at a seminar, or I happened to see him at a freshman camp on Catalina Island or whatever. But on this occasion, I was sitting in my office and I got a phone call, and it was from Feynman, and he wanted to know how well we understood Earth's gravity field. And the reason he was asking is that he got interested in what was then called the fifth force. The fifth force was the term that was used for a modification of Newtonian gravity. This had nothing to do with general relativity. It was just a purely classical, essentially classical notion about an additional contribution to gravity that came from particles of finite mass, whereas gravity as we understand it is mediated, we think, by things that are massless, and so the signal goes at the speed of light and so on and so forth. Now, if you have something that's massive, then the potential becomes Yukawa-like, and so it has a finite range. And at that time, there were people advocating this based on geophysical measurements. There were people who thought they saw evidence for this by measuring Earth's gravity field as you went up some high tower above the Earth's surface, people who thought that gravity changed when you went down in a submarine in a way that was not explained by conventional Newtonian gravity. And so Feynman wanted to know how well we actually knew gravity. I'm not an expert in the subject, but he just reached out to the person he knew. And so I remember going away to the library and actually reading up on satellite measurements and telling Feynman the accuracy with which these were made. He made a suggestion to me, which was never followed up. And his suggestion to me was to use a low-flying airplane in some place, such as upstate New York. He actually said that, where you could basically map out Earth's gravitational potential, in effect, by doing a lot of measurements in a cube, a fictional cube, not an actual cube, but just a set of points in Cartesian space. And in that way, you could test the basic ideas of Newtonian gravity. So that was his suggestion. It's an interesting one. Nowadays, I think we could do better. I'm not sure that anyone has really followed up on this, the main reason being that the fifth force went away. People realized that the claims for the fifth force were based on things that they didn't fully understand, like the fact that salinity in the Earth's oceans actually varies, and that changes the gravitational signal that comes from water, which was previously assumed to be constant density. And so, these were small effects, but understandably of interest if you thought that there was some deviation. By the way, if gravity were more complicated than inverse square, that would be profoundly important for the way you thought about planets, the way you thought about satellite orbits and so forth. You have to remember that when people quote the mass of the Earth or the mass of any celestial object, they're actually assuming that we know the gravitational force, and specifically that we know big G. Big G, Newton's gravitational constant, is measured in the lab. So you can measure Earth's gravity to 1 part in 10 to the 12, but that doesn't tell you the mass of the Earth. You still have to use big G. You still have to know what the force is. So it's actually of some importance to establish whether Newtonian gravity is correct. This idea was still around in later years because there were people who I knew at JPL, for example, who wanted to say that spacecraft that were leaving the solar system, the Pioneers and Voyagers leaving the solar system, were exhibiting a change in their velocity, acceleration. that was inconsistent with Newtonian gravity. Turns out there are other non-gravitational effects, but that explains perhaps why this is an interesting question.
So just to be clear, the conversation with Feynman, did it concern the Challenger itself? Was that part of the discussion?
No. So I'm sorry. I mean, it was a slight digression, but I only made it to explain something that happened to me, which is that I never talked to Feynman again.
I see.
But as for the Challenger disaster itself, I saw it in real time on television in the building, the very place I'm sitting now, and I saw it with Jonathan Nudin, who at that point was a former student of mine who happened to be visiting because he was part of a committee that met at the boardroom in the Millikan Library that morning. And so we were sitting there together and watching this thing take off. I wasn't a big fan of the shuttle, he was, and he knew that something bad had happened. I was just looking at it and not knowing what was going on because I didn't know what to expect, but he knew immediately that something bad had happened. So that had an effect. Of course, it didn't directly affect my science. Indirectly it did, because of course, it led to a change in the timing of the Galileo mission, which had previously been scheduled for launch soon thereafter, and they had to delay that and do it in a different way. And so we didn't get the scientific return of the Galileo mission until almost a decade later.
Dave, to clarify, was the Galileo delayed because there were similar safety concerns, or just because everything was in haywire at this point?
It was delayed because you could no longer use the shuttle to do the launch.
Mm-hmm.
So the intent was to use the shuttle as a means of getting to Earth orbit, and then the Galileo spacecraft would go beyond that. They instead had to launch it from the ground and much later. And so there was a delay. I don't remember the details anymore, but certainly the absence of of course, the shuttle eventually got back into business, but there must have been safety concerns as well. I don't remember the details anymore. It just meant that Galileo was launched much later.
What was compelling to you as Galileo got off the ground? What were you interested in its findings?
My approach to science at that time was not heavily tied to what we were going to learn in future missions, but it's certainly true that when the information came back from Galileo, it had a big consequence for the science I was doing. Perhaps the most important was the confirmation. We already thought we knew this, but it was confirmation that helium was depleted in the atmosphere of Jupiter. So Galileo had a probe dropped into the atmosphere. That was early in the mission. And everybody understood that it was important to measure the helium abundance to great accuracy. So it was done by two different methods. The methods agreed, and it showed that there was a 10% depletion of helium. It also measured other constituents. It showed that heavy noble gases were enriched. It showed that neon, which is a light noble gas, was strongly depleted. So the behavior of helium and neon agreed with my theoretical ideas. It was a confirmation of what I had been saying back in the 1970s. So that was one thing. The other thing was a completely different story and had to do with the magnetic field measurements of the satellites. The Galileo spacecraft, after dropping off the probe into the atmosphere, wandered around the satellite system, giving us spectacular pictures of the surfaces, some of which we already knew about in less detail from the Voyager mission, but in particular, it got close enough to the satellites, the icy satellites, and to Europa to measure magnetic field. And it found near Europa that the field was greatly changed by Europa. Europa is in the magnetosphere of Jupiter, and I set about, actually with a Physics 11 student, to try to understand those results. There were people at UCLA responsible for that part of the mission who had also worked on this, and as best I could figure it, had dropped it. They had not been able to understand the results. But I started working on this. The Physics 11 student did not actually succeed in figuring it out, but I figured it out after he finished his summer's work, and realized rather quickly that the magnetic field near Europa could be explained by electromagnetic induction, essentially by eddy currents. Europa, like the other satellites, experiences the time variable part of Jupiter's magnetic field arising from the dipole tilt. And that time variable part, according to Faraday, must induce an electromotive force inside any conductor. And this is a well-known physics effect. It was studied way back in the 1800s. And of course, Faraday was even earlier. And so I realized that Europa was behaving essentially as a diamagnet, meaning that it excludes field perpendicular to its surface, which is exactly what you expect from conductors. So the question is, what is the electrical conductor inside Europa? And you don't need a very good conductor, it turns out. You just need an electromagnetic skin effect, and you can do it with salty water. And salty water is a natural thing to think of. In principle, you can do it with graphite, but it doesn't make sense to have a continuous sheet of graphite. There's no chemical reason to have such a layer. So the natural conclusion is that Europa had a salty ocean. And that's what I decided. I actually gave a seminar on this in planetary science at Caltech. And it's funny in retrospect to think that when I did this, I never thought of this as being particularly remarkable or especially interesting or anything, because the idea of an ocean was not entirely new. But I should have realized that having an observational constraint like that was important. Anyway, I wrote it up. I sent it off to the people at UCLA and forgot about it until they contacted me months later and saying, would you like to be co-author of a paper on this? So ended up in Nature. So it's slightly embarrassing to think back at an example of something I did where I didn't realize how important it was, because nowadays, of course, the idea of an ocean in Europa plays a major role in our thinking about oceans in general and a motivation for the Europa Clipper and so on and so forth. I still think that we have the best evidence for an ocean in Europa. People look at the surface and say, well, look at all that broken up ice, chaotic terrain. Doesn't that mean you've got an ice shell floating on an ocean? Well, it's consistent, but geology is a tricky way of deciding whether you have an ocean. Electromagnetic induction is the best way to do it. And of course, the big surprise, which I didn't realize, was that it's also true for Callisto. So there's a certain irony in that. Europa is special. The ice shell is thin. It's a more attractive environment for thinking about life elsewhere in the universe, perhaps, certainly in our solar system. I mean, Mars is the natural one to think about, but Mars is boring. It's like the Earth. Europa is different. So it's an interesting idea. But Callisto has an ocean as well. I look back at it now and I say, well, yes, of course. I sort of even knew that that's a possibility, but your views of science change over time, and you come to realize how things fit together in a way that you might not have realized quarter century ago. And this is 25 years ago.
Dave, an overall question, bridging chronologically the 1980s to the 1990s, is that your sense of the budgetary environment for planetary science. On the government side, for example, did you feel the impact of Reagan's increased military spending? Did that spill over into planetary science? And consequently, at the end of the Cold War, was there a pullback in budget? On the private side, today we know, of course, about people like Jeff Bezos and Elon Musk and their impact on planetary science. Was there such a thing as the billionaire or 100-millionaire private benefactor who could bestow gifts that really were capable of changing the field in the 80s and 90s?
So planetary science underwent major changes through those decades because of the funding, which at early times was almost entirely the government, NASA or agencies in other countries. So in the Apollo era, of course, as a political imperative, there was a huge amount of money spent. And of course, most of that went into building the spacecraft and so forth and actually getting to the moon. But some of it also went to scientists. And so you have people studying the rocks and so forth. And then there was a dramatic drop-off in support for that kind of science, including what we would now call planetary science through the late 70s and into the 80s. And the decline of the budget led to the stretching out of the timetable for sending missions and so forth. And so I think it's fair to say that in the 80s through the 90s, there was this general sense of diminished activity in planetary science. It showed up in the number of students interested in pursuing the field. It showed up in the pace at which new results were made available. The Voyager missions were spectacular. Galileo did well. We had Magellan to Venus, which I was not involved in, so it's not as if there was nothing, but there was less per unit time than there is now. And there were no sugar daddies. There were no rich billionaires who had money to throw away, as we have now. Stunningly wealthy people like Bezos, or even for that matter, somebody like Elon Musk. It just didn't exist. By the way, I think those people are remarkable. I think they did something special. They added value to the world economy. So I don't want to take anything away from them, but they did not exist. So what happened? Probably the most important thing that happened in the history of the subject was something that we now recognize as a mistake or a misdirection. And that was Alan Hill's 84001, which revived exploration specifically for Mars. Alan Hill's 84001 was a meteorite from Mars that was picked up in Antarctica, and that's why it's called Alan Hill's. And some people claimed in a prominent paper that it showed evidence for life. It doesn't, although some people may still disagree, but it certainly revitalized the science. It got people very interested in life on Mars. There were other things happening, but in general, as you went into the first decade of this century, there was an improvement in the budget, and that has more or less continued. And it's not tied to whether you have Republicans or Democrats in control. And I'm not even sure I'm in a position to explain exactly why this was happening, except to say that I do know from personal experience that there are some people in Congress who love the idea of life in space. So that's certainly part of it. So I was part of a group a decade ago that mapped out the future of planetary science. This is called a decadal survey, and it's done every decade. There's one taking place right now, which I declined to be involved in. And so that survey, like previous ones, it was begun by the astronomers, but that survey in planetary science attempted for the first time a decade or so ago to construct a budget consistent with what we thought would be the amount of money available. And And so we had what's called a budget wedge, and we had to try and fit missions into it. And it led to some important decisions like downgrading the mission to Europa so that it would cost less, downgrading sample return from Mars so that it would cost less. These things are now becoming more expensive, but other things are happening, and there are cheaper missions happening, and the budget has grown. And as best I can figure it, the growth, which is real dollars, there wasn't a lot of inflation in the last decade, maybe there will be now, but in the last decade, inflation was modest. The budget in real dollars has grown. Science has become more expensive, but we're doing a whole bunch of things. There's a vibrant community, and I'm not sure I'm a big fan of why it is happening, but as best I can figure it, it is this enthusiasm for life.
Dave, the last subject I'd like to touch on for today, and that this is to foreshadow to your tenure as division chair, is if you can explain administratively the overall structure at Caltech and some of the idiosyncrasies at the Institute. So, for example, what is the difference between a department chair and a division chair, and what might we call deans, even though we don't use that word in Caltech, in understanding relatively how much power is contained in these administrative responsibilities?
So Caltech is small. It does not try to do everything. It has things that we call divisions. At other institutions, you might call them departments, but perhaps an important distinction to make is that what we call a division is a combination, in many instances, of things that elsewhere would be separate departments. The best example of that would be physics, mathematics, and astronomy, which we call PMA. At most universities that aspire to excellence in those fields, those would be separate departments, completely separate, subject to some dean. At Caltech, we have maintained a leaner structure. We have 6 divisions. We have no desire for more than that. I happen to be in a division, geological and planetary science, that is not that different, actually, from a comparison department at MIT, which is called Earth, Atmosphere, and Planetary Science, EAPS. I like to call it the Department of Everything. So the structure of the part I'm in is not hugely different from other places, although to be sure, there are places that have a different structure, and Cornell is one of them because Cornell has put planetary science in with astronomy. We have the astronomers separated out into a different division. They happen to be across the road, and of course, there's a lot of interaction, and that's one of the good things about Caltech. So, main point about Caltech, the administration is lean. There are division chairs with substantial budgets and a great deal of power that comes with those budgets. There are no academic deans at all. This makes us different from every other place I know about. I think this is a strength. It means that at Caltech, the decisions about who to hire and the most important decisions about the academics, which have to do with promotion to tenure and so forth, that those are done by a small group of people. And the group I'm referring to is called the Academic Council, Institute Academic Council, and it consists of the 6 division chairs, the provost, and the president. And in that particular group, the provost is very important. The provost is responsible for the academic part of the institute. I think we benefit from that structure. I know from looking at what happens at places like MIT or Harvard, that one of the benefits is proximity, the sense of having a connection with the important decisions. whereas elsewhere you get the feeling that professors are not so closely connected. They're not as aware of what is going on. I'm exaggerating a little bit. I'm not sure to what extent this is universally true, but it's certainly the sense I get, having spent some time at Cornell, where I'm a professor at large, and having been on a visiting committee at MIT, where I see the interaction between the deans and other people high up in the administration who are viewed as remote by the professors. At Caltech, you actually see these people who are at the top.
And so, as full professor from 1984, it would probably be fair to say that in the intervening 5 years, you were already at a position of seniority where you saw how these things worked at the Institute.
Yes, I could see how the Institute functioned, and I thought it was accessible, and that's a benefit.
Scientifically and administratively, you're saying?
It's a benefit scientifically and administratively, but I'll say it now, although we may get into this later, that I actually think that a desirable thing, certainly at Caltech, is to have an administration that doesn't do much, stays out of the way. Because after all, the essence of a place like Caltech certainly is the excellence of individual scientists. And that's what you want. And so you want to be in an environment where the existence of the administration is not pervasive. It's actually better that it be, so to speak, invisible. That it's better that you just do your own thing and do it well. I have to say that I'm not so sure that this is true anymore, but it's certainly the way Caltech used to function.
Dave, that's a perfect place to pick up for next time when you decide to become division chair. So we'll cut it there.